Good morning. I'm John Rundle. Normally you would see Chris Wood up here moderating this, but he is recuperating back in Santa Fe from an illness, and we all wish him the best, and we wish he was here. Hi, Chris. He's watching, I think, on the video. So today we have a truly exciting program with some incredible speakers, and their bios are on the table back in the hall, and it would take probably longer than this meeting to go through the qualifications and the accomplishments and honors of all these people. So we'll do that only briefly. But what I'd like to do first is start the proceedings off by introducing Michael Mauboussin and Marty Leibowitz, who will give you a welcome. The first one will be, I think, Marty from Morgan Stanley. And again, we're very thankful for the continued use of this facility. So, Marty.
We at Morgan Stanley are delighted to be hosting, once again, this important Santa Fe Institute symposium. This symposium has been increasingly popular over the years. We're now at totally full capacity, and there are many others in the one of the side rooms trying to see what we're doing on video. So this is a symposium on topics that both are and will be of increasing importance in our day-to-day lives and in our future careers. The speakers that we have are ones who have not only thought outside the box on these topics, they've thought well outside the FedEx van that delivered the boxes. So I'm a great fan of brief welcomes, and with that brief welcome, I'll turn it over to Mike.
And also on behalf of the SFI community, I want to welcome everybody this morning. Well, as you all know, by the way, Marty is one of the all-time greats in this business, and I can think of no one who's contributed more to our industry or who's more respected by his peers. So I want to also thank you, Marty, for your outstanding support and help as a co-organizer. So thank you, Marty, for everything you've done. And I also, of course, want to thank Morgan Stanley for their generosity. We've been doing these risk meetings in New York for quite a while now. I think we're over a dozen years in a row, and we've had some really wonderful speakers over the years. And these over the years have included Benoit Mandelbrot, we've had George Soros, we've had Peter Bernstein, Henry Kaufman, Nassim Taleb, and we have an absolutely spectacular lineup again today, including the winner of the 2002 Nobel Prize in Economics, Danny Kahneman. So we should have a really fun and stimulating day. So it's my pleasure to kick us off, and that is with to introduce the new president of the Santa Fe Institute, David Krakauer. In my first term as chairman of the board, I knew that there was one major task, and that was to hire a new president for the Institute. And we are thrilled that we were able to have David join us, started at the beginning of August. He is, as you will see in a few moments, an extraordinarily rare combination of intellect and I think very good taste, and good taste in science and lots of other things. And I can say, I think speaking on behalf of the board, we are thrilled to partner with David in taking the Santa Fe Institute going forward. So David, turn it over to you.
Good morning. Good morning. Thank you, Michael. Thank you, Marty. Thank you, John Rundle, wherever you are, over there, for inviting us. Before I start, I just want you to point out this truly extraordinarily beautiful poster that we designed for the November meeting, and this is really in honor of Bill over there, who sort of likes to think of his world in terms of science fiction. And there you see, you can't see it clearly, but there's a Bitcoin there represented as a comet that's about to wipe out all financial life on the planet Earth. So we'd love to see you, as many as you as possible, at the November meeting. So I am going to talk about big data, what, why, and that strange archaic adverb, whither. And in trying to get together the ideas for this talk, I found the quote by Mark Twain that best encapsulates, I think, the issue, for me at least, and it's this. It's not the size of the dog in the fight, it's the size of the fight in the dog. Okay? You all know that's true, and when we say big data over the course of today, I want you to think big dog. And is big dog what you mean, or is it high quality information, right? Is it a very strong signal? And of course, you can have a strong signal in small data. So it's not the bigness of the dog that matters, it's the fight in the dog that we care about. Now, before I talk about big data, I need to talk about what big is and what small is. You know, if you think about it, if one of your kids came to you and said, "Mummy, Daddy, what does big mean?" You'd punt. You'd say, "Well, I know what bigger means, or smaller, but I'm not sure I know what big means." So I'm going to give you 3 examples of what big and small might mean in an absolute sense, just to get us going in a sort of SFI style. So the first one, in relation to dogs, is in physics, right? So there is a real sense of big and small if you talk about the quantum mechanical realm and the classical realm. So Heisenberg's uncertainty principle applies in the quantum mechanical domain, this idea that you reduce the uncertainty in position, you have to increase your uncertainty momentum. That's absolutely not true in the classical domain. And so this is a real distinction between big and small that exists in physics. It's not clear to me it's useful in finance. George will tell us if it's useful in finance. But it is a distinction that's worth being aware of. Another distinction, which is extremely boring, of big and small, has to do with the amount of data required to reach a desired level of statistical significance. That's the one that everyone in the room knows. And Fisher gave us this rather arbitrary notion of what a significant threshold would be, for example, the 95% significance level. And you need enough data to reach that threshold. So it's discontinuous by virtue of imposing an arbitrary threshold on a continuum logic. The most interesting one comes from my colleagues at SFI, and of course it's not surprising that I would say that. And that comes from allometry, the theory of scaling. And so many of you will know, you've probably heard many times from my colleague Geoffrey West, that there is a universal law in nature, and that if you plot the mass of an organism against its metabolic rate, it doesn't surprise you that there is a positive correlation between the two. If you're bigger, you use more ATP. Right? What's surprising is that all organisms fall on the same universal function, which is a power law, where you essentially get metabolic rate scaling as mass to the 3/4 power. And if I showed you a plot like that and said, what is big and what is small, you might say, well, big things are on the right-hand side. But you can see that that's somewhat arbitrary, because they're all essentially following the same underlying universal law. There's no notion of big and small here, right? More interesting would be to say big is a violation of the underlying law. That is, a residual from the underlying curve gives you your sense of big. And so, for example, if you look at human beings, we have a body mass on average of about 100 kilograms, and we have an energy usage of about 100 watts, like a light bulb. But if you factor in the amount of energy we use, for example, from fossil fuels and so forth, in fact, human beings have an energy usage of about an order of magnitude larger, about 10 kilowatts. Okay, and if you ask what size is a human in terms of the living world, that is, in terms of an organism that would use that amount of energy, human beings would be a tantamount to the scale of a blue whale. So that is really a notion of big, because we violate an underlying universal law. So that the 3 notions of what big might mean that are a little bit more principled than bigger. So now let's talk about big data. What is big data? Well, in 1980, when I was programming, that's not me, by the way, when I was programming the Commodore 64, 8K was big. 9K was infeasible. Okay? You couldn't do anything with 9, you just couldn't do it. I didn't have the random access memory. In 1982, when the Commodore 64K came out, 65K was big, right? And the fact is that the increase in memory and data availability has been following a constant universal law for the last 35 years. There is no point, say 5 or 10 years ago, where data all of a sudden became big. It's just been growing at some more or less constant exponential rate for several decades. So if that's true, what do we mean by big data? Where is the excitement coming from? Well, one possibility is not the data size itself, but the economics. So for example, if you look at genomics, in 1995, it cost about $1,000 to sequence a single base of DNA. Okay? because of Moore's law largely, which more or less saturated in 2005, but that's another conversation, by 2005 it cost about $1 to sequence a base. And as of 2015, it costs about 1/10 of $1 to sequence a megabase. That's 1,000 bases. So maybe what we mean by big data is the combination of large storage at very low cost. It's continuous, but it's better than just the capacity. Another possibility, for those of you who are at Morgan Stanley, is something like this. It's a little bit my experience with the VIC-20 or the Commodore 64. In 1995, Excel was based on a 32-bit architecture, and there was a maximum file size. And many of you will be familiar with that. But since it became 64-bit, it essentially has no hard limits on the maximum capacity any longer. So maybe that's what you mean. The software that you use to represent the data that you work with is no longer, in some sense, limiting with respect to what you can analyze. But the most interesting, and I think it's the reason why we're here today, is coming from advances in algorithms, and in particular, classifiers. And I'm sure some of you will talk about that, but the one that everyone's getting very excited about, and certainly Google get very excited about, is deep learning. And this is quite interesting historically, by the way, from those of you who are interested in the invention of technologies or the rebirth of technologies. In the 1950s, engineers became very interested in neural networks, largely because of von Neumann's work, a posthumous book, The Computer and the Brain. And they invented what they called then logical automata, or perceptrons, simple neural networks. The problem is there were certain elementary Boolean functions that they couldn't compute, and so they were neglected. They came back in the 1960s and 1970s as parallel distributed processing. You remember those 2 volumes by McClelland and Rummelhart. And they died about 1990, because even though they were interesting ideas, they didn't play well with data. And then in the late 90s, 2000s, I guess, when the trends which I've described started to emerge, computing power got cheaper, computers got faster, data sets got larger, all of a sudden, problems that formerly we couldn't solve were solvable. And the best known problems are visual recognition tasks. So basically what classifiers do is they take some unstructured data, for example, visual data, which when it's projected on your retina, just looks like variation in the intensity of light, and they systematically create features at higher levels. So you go from an inhomogeneous field to edges. That's the second panel down. Edges are assembled into simple motifs like eyes and ears and noses, and they're assembled finally into faces. So these kinds of deep learning networks do things like complex hierarchical feature detection. And that's what they look like. Starting at the left, you have lots of little nodes. They pick up variation in the input, and they systematically aggregate into higher and higher features, ultimately culminating, as Google told us, in cats. And so this is the point where if you present these deep learning networks with lots and lots of images online, you ask them, what are you seeing in that large data set? Eventually they say, well, the thing that we see over and over and over again is cats. If it had been me, it would have been a pit bull, and others have their favorite dog. But that in itself is not that interesting. What's interesting is this. So this is the work of Marion Bartlett at UCSD, and she asked the following question. She said, could I train a classifier to tell me when someone is either not experiencing pain, is truly experiencing pain, or is faking it? Now this is quite complex. It seems like a highly socially mediated cognitive mechanism. And yet, when you train these deep learning networks to make discriminations, and you compare them to the performance of very highly trained humans, this is what you get. Humans perform essentially at chance levels. So if I fake an expression of pain, you can't tell the difference between that and me truly experiencing pain, for example, in a committee meeting. Okay. Whereas a computer gets it right 85% of the time, which is extraordinary. And maybe this is really what we're here for, because these machines are now finding complex patterns that humans cannot find. So very high dimensional data sets. And maybe this is the most important point, of course, because you're all thinking financial markets, whereas Marion is thinking facial recognition. That, I think, is the ultimate reason we're interested. But I want to end with a sort of a cautionary tale of why this ultimately is going to be woefully insufficient moving forward, and why we need an entirely new framework for studying the kinds of data that these algorithms are being thrown at. And this is the whither, or the risk of big data. So I'll just give you an example from the history of physics. So if any of you collect astronomical instruments, and maybe one or two do, you see someone's laughing. Who's laughing? Mark, you do. Okay, so maybe you this is in your collection. So these are armillary spheres. So these are beautiful little mechanical models of the solar system, going back to essentially the 8th century through to the 17th. And what you see is that these models of the universe are getting more complex. And the reason why these models are getting more complex is because the data was getting better. Right? More and more observations were being made, and to accommodate the observations, you had to build a more complex model. The reason why these models were so problematic is because of two fatal assumptions. The first assumption was that the Earth was at the center of the universe, and the second, more subtle assumption was that all orbits are circular. And if you think about observing the motion of the planets under those two assumptions, they behave in very erratic ways. And the only way that you can reproduce the apparent motion of these celestial objects is through essentially an infinite Fourier series. You have to add, the greater the precision of your measurement, the more and more and more and more periodic circular orbits have to be added. So the model becomes infinitely complex in the limit of perfect observation. Okay? And this is where we are, right? This rather stupid, I don't know what he is. He's not a Neanderthal, because we're told that they were smarter than us. Some kind of proto-hominid trying to fly a dead tree as if it were a kite, using his extraordinary might. This is essentially where we are, right? In other words, the very big data sets with a not very intelligent choice of basis set requires very big models. And what happened in the history of physics that reversed the trend of outrageously expensive, mechanically unstable armillary spheres? Well, here's Tycho Brahe. He's a wonderful astronomer. Many of you will know him. Danish. Had a gold and silver nose. He had a bimetallic nose. He lost his nose in a duel with a mathematician over who was the better mathematician. Mathematicians are a little bit childish, if you've ever met any. And that's the Tychonic system there on your right. But Kepler made extraordinarily good observations, and so he built very large models. But he had the great fortune of hiring a really smart postdoc, Johannes Kepler. And Johannes Kepler said, you know, the orbits are not circular, they're elliptical. And the thing about ellipses is you can reconstruct orbits with a pencil and rope, rather than having to rely on an entire monastery to reconstruct exquisite circular orbits, which are in fact wrong. So this was a huge advantage. Kepler achieved enormous simplification. He also could fit the data, but he could fit the data with a much smaller model. What he did was not improve the fit to the data. What he did is change the underlying structure of the model. And then Newton came along, and we could talk about Newton at great length, rather angry person, and very, very self-centered person. And he said, you know, Johannes has no idea where these elliptical orbits come from. That's as bad as the earlier model. It's simpler, but it doesn't, what's the mechanistic basis of the ellipse? And so we have the inverse square law of gravity. And the wonderful thing about gravity is that it demonstrates that the ellipse is only one of the possible orbital solutions. In fact, as Newton demonstrated, there are many alternative orbits. And not only elliptical, not only circular, you could get circular in a limit, but parabolic and hyperbolic orbits. So for example, if you have a rocket ship that has some thrust, the orbit is no longer elliptical. And so the important point of this story is that big data analysis will not, according to the current trend, ever discover mechanism, it will never generate theory, and it will never predict violations. So what Newton did by generating a more fundamental mechanistic theory of gravity is demonstrate that the circle and the ellipse that preceded him were just special cases that arose from a fundamental principle. Okay? And this is ultimately because humans are not very smart. The fundamental constraints of human cognition means that we have to be ingenious. What we're doing with very powerful computers is being Bob, the big, dumb, lumbering caveman, right, who's trying to turn the dead tree into a kite. And the place that thinks most carefully about this is the Santa Fe Institute, where we try to conjoin, right, the algorithmic with the mechanistic theory, the fundamental theory, attending very carefully to the reliable, hopefully, data. And thank you very much.
Any questions or comments?
Yes.
Yeah, if I recall correctly, Kepler spent years studying the data
On Mars. Mm-hmm.
to try to find, before he came up with his famous laws, to find not just the ellipse, but also the basic sweep of the ellipse through time. And he was, I think, well, first of all, could you comment on that?
Yes. Yeah, so this, Marty is pointing out that Kepler didn't just stumble upon the solution. He spent years, in fact, he spent years and years looking through Tycho Brahe's data. In fact, Brahe didn't want him to. As you know, they had a very fraught relationship, and I think Brahe recognized that Kepler was smarter than he was, and tried to withhold some of the data from him in order that he wouldn't discover a simpler mechanism. So it does take an awful long time, and I think this, Charles Peirce, the great philosopher, American philosopher, pragmatist, called this process abduction. So we're very familiar with deduction, that is how you move from one step to another by following a formal rule system. We're familiar with induction, which is generalizing from empirical experience. But how you arrive at a truly novel insight, he called abduction. And I think it's something about which we know very little. And that's what Kepler did. Very good. Thank you very much.
Thank you, David.